So I was asked to talk about cosmology, and of course, cosmology is a huge field. What I've decided to do is basically to talk about the standard cosmological models, and I will focus on the hypothesis of these models and say what kind of constraints we can get on how good these hypotheses are. Of course, I've put open possibilities. This is a very attractive things to put in a title, but as you guess, I cannot discuss all the possibilities, but I will try to give some hints of how we will have to extend our standard cosmological models. And also I've decided to put the emphasis on some works and discussion I had with George Ellis, because he is I mean, the main person in this workshop. So this has guided, I mean, the topics I have chosen to discuss today. So I think that for me, when I do physics, I'm a theoretical physicist, the most important things when I'm dealing with a theory or with a model is the limit of what this model can explain. I think this is something very important when you are teaching physics. And I remember when I was a kid, you learn about laws of physics, like Maxwell laws, and they are given like something which are written on marbles. And then you start to do research and you realize that any theory is coming with a domain on validity and hypothesis. And this is basically, as a researcher, what is interesting, is what is the limit of the model and of the theory you have, because this is where you will have to, you will be able to make new research. So when we talk about cosmology, on one hand, we try to construct a model which is coming from taking into account the laws of physics that we know, theoretical physics. And these theoretical physics law, usually they are based on principles, and they have been validated locally here on Earth or in the solar system. On the other hand, we want to talk about the universe, and we have many observations coming from astrophysics. And a good cosmological model will be a model that will be able to reproduce, I mean, this astronomical data. I mean, this is a basic constraint. It has been discussed by many historians, among them Pierre Duhem. And you know that if you just think about the model of the solar system, if you come some centuries ago, there was a basic discrepancy between the theoretical approach and the astrophysical approach. In our standard cosmological model, basically we will have to assume for theoretical physics that gravitation is well described by general relativity. That will be my assumption. And the matter content and the non-gravitational interaction are described as a standard model of particle physics. And once you know that, you have made a hypothesis, which I call number 1 and number 2, which are hypotheses on theoretical physics. And then it's not enough, because these laws of physics, they are too complicated. They are usually partial differential equations which are nonlinear and coupled, so you cannot solve them in their full generality. And you are trying to look for solutions of the theories which are good representation of our universe, and for that you have to assume some symmetry hypothesis for your solution. And the working hypothesis is a Copernican principle, stating that we do not live in a particular position in the universe, and this leads to the construction of models which are spatially locally homogeneous and isotropic. And then once you construct this kind of model, you still have one more freedom, which is the global structure of your universe. You have the choice of a topology, and usually we assume that topology is trivial, which means that if the space is locally Euclidean, it has to have an infinite volume. But there is still a choice in this possibility. And this model, in which you have to add 2 ingredients, the first one is called CDM, cold dark matter, and the second one is the famous cosmological constant, is in agreement with all existing data today. And this is, I mean, the main puzzle now is that we have to use 2 main ingredients, the cosmological constant and the cold dark matter, but the existence of these 2 components are basically derived from the fact that we think that general relativity is a good description on gravity on the scale of this phenomena. So this fact that we need for what we call the dark sectors, this cold dark matter and these cosmological constants, has pushed most of the astrophysicists and cosmologists to come back to say, well, basically among all these hypotheses, how much can we trust this hypothesis? So once you construct this model, basically you will have different kind of systems, and here is a timeline of what the universe looks like. And you see, at late time, basically, we are working with non-physics. If I start from BBN time, which is basically 1 second after the Big Bang, then I'm just using nuclear physics that is tested in accelerators and electromagnetism. The CMB is physics as 3,000 or 4,000 Kelvin, which is also very well tested. And this is the first interesting point. So we are working with non-physics, and also we are working with physics in a linear regime, which means that we don't have like complex behavior and complex systems. At late time, because we have formation of the large-scale structure of the universe, we are entering non-linear regime for gravity, and of course we don't have any analytical solutions for our theory. If we go backward in time, then now we have problem with the physics because we are using a microphysics which is not understood. So this is another limitation. If we want to describe the primordial universe, we have to discuss about the reheating, how are the particles produced after inflation, or baryogenesis. This is something which are open fields because the microphysics is not known. If you go even further, we will need some phase of inflation to fix our initial condition, and it relies on the existence of a scalar field, which is completely speculative at the moment. No one has seen any scalar field in an accelerator. And if you extrapolate more, you come to other structure like the multiverse structure, like quantum gravity structure. So you see there is a whole extrapolation when you go backward in time. What is interesting here is that basically we managed to have a good understanding of our universe, and I think it's mostly because we have a property of these laws of physics which I will call scale decoupling. I think it's related to what George was saying, is that at this step we have different levels, but we observe that there are energy scales below which we can construct an effective theory which allow you to deal with this particular phenomena. When I'm doing nuclear physics, basically I don't need to know anything about string theory. This is completely irrelevant. It means that there is these different levels, they are separated in some sense. And this is something which is not well understood, and we can ask why are the laws of physics, have the laws of physics these properties. BBN? Oh, Big Bang nucleosynthesis. Big Bang nucleosynthesis. So, in my previous slide, you see that the cosmological scenario basically describes the complexification of matter while the universe is cooling down because of the expansion of the universe, and it will only develop nonlinear structure at late time. What is important is usually if people are focused on the Big Bang, I mean these singularities that exist, and I think it's not very important in this model at the moment. What is important is that we control the initial stage from observation. We know that the universe has to emerge from an initial stage which is very hot, very dense, and at thermal equilibrium. This is something we will have to explain. And now I would like to connect this with this cosmological scenario with the hierarchy of structures that has been proposed by George, where he's basically talking about the different description of science and going from more fundamental to higher fundamental. And I would try to make a connection between the cosmological scenario and this hierarchy of structure later on. So when we look at the universe, we have a basic constraint. We cannot observe the whole universe. We have a limitation, and this limitation is coming from the fact that we are observing the universe from a particular point in space-time, and today we are mostly observing the universe through electromagnetic waves, and they have to propagate at the speed of light, which means that all the information we get from the universe is coming from our past light cone. And of course, because we have an initial singularity, it means that we can observe only a finite part of the universe, which we call the observable universe. We can get data from this part of the universe. And from these observations, we want to say something on the universe as a whole. So one of the questions we will have to deal with is how representative is our local universe of the universe as a whole. So now, as I said, the dark sector, dark matter and the cosmological constants reveals the need for new degrees of freedom in this cosmological setting. Usually it's introduced a new matter fields. But we can ask the question whether this is related to a modification of general relativity on astrophysical scales, or whether our symmetry hypotheses were too drastic and we have to go beyond the Copernican principle. So I will try to describe some of the tests that have been proposed to test general relativity on astrophysical scales and also to test the Copernican principle. And then I know, because I know George has a huge interest in that, I will talk about the topology of the universe and progress we may expect in the coming years with the Planck satellite. So astrophysical test of general relativity. So first, what I mean by general relativity is that I have a theory of gravitation which is based on the equivalence principle, the university of freefall, local Lorentz and position invariance. And if I have this equivalence principle, then I can deduce that all matter fields have to be universally coupled to a metric tensor. So the action of matter is completely determined. Then I need a dynamics, which I choose usually to be the Einstein-Hilbert action for another metric, which I call G stars. And in general relativity, you have these two metrics to agree together. The dynamical metric and the physical metric are the same metric, and this is the form of the equivalence principle in its strong form. Once you have that, you get your field equation, which are the so-called Einstein equations. So this is basically a summary of what general relativity is on one slide. So you have tests of general relativity in the solar system, and you know that we cannot allow deviation for more than 1 part in 1,000 in the solar system. The question is how far away from general relativity we can be on astrophysical scales. The point is that if I make a parameter space to try to understand where I need to modify general relativity, I can use two parameters, which is the gravitational potential and the curvature scale. And you see the solar system is this small dot and dash in the upper right corner. And the places where we infer the presence of dark matter and dark energy, assuming general relativity, is in a very low curvature regime that is not tested in the solar system. So this is a very important point. And so this is why we cannot infer from the test of the general relativity in the solar system the fact that it applies as such for galaxy rotation curves, and also to explain the acceleration of the universe. So let me try to give you the idea of one of the tests which is now implemented to test general relativity in the solar system on astrophysical scales. And it's basically a generalization of what has been done in the solar system. So one of the historical tests of general relativity is to use the light deflection by the sun. What is interesting is that if you just use the light deflection, basically the angle of deflection is given by the Newton constant and the mass of the sun. So in order to say that what you measure is compatible with general relativity, you need to know the mass of the sun, which you did because on these scales, the general relativistic dynamics is equivalent to the Keplerian dynamics, and you can use the Kepler law, which tells you that you have another determination of the mass of the sun once you know the period and size of the orbits of the planets. So you see, in fact, what you are doing is that you are using two determinations of the mass of the sun, one from the lensing effect and one from the dynamics. And what you are testing is whether these two estimations of the mass agree together if you assume general relativity. So we can try to do the same thing on astrophysical scales, and for that we will use an effect which is called weak lensing effect. So you have background galaxies, and the light from background galaxy has to propagate in the universe where you have a lot of density fluctuation due to the large-scale structure of the universe. It means that the shapes of the background galaxy will be distorted because you have tidal effects. So first, from the matter distribution, you can infer the total matter, so the source of the gravitational potential. And from the weak lensing, so this is a magnified picture of the distortion of the background galaxy. For the shape of the background galaxy, you can measure the gravitational potential itself. So you can ask yourself whether what you see from the matter and what you measure for the gravitational potential agree together. So that was the driving idea of this test. And basically, the idea is to use, if I simplify everything, I can use the Poisson equation, which relates the gravitational potential and the density contrast of the matter. Weak lensing is a way to measure the gravitational potential, while galaxy catalog is a way to measure the density fluctuation. So you can ask yourself whether these two kinds of observations are compatible together. What is interesting is you can also measure the motion of the galaxy, and the motion of the galaxy is also related to the gradient of the gravitational potential. So there is a third observation which allows you to have very strong constraint on the deviation from general relativity. So interestingly, these things will be probably measured in about 10 years from now. There is a satellite which is called Euclid, which has been accepted by ESA about 10 months ago, and will be launched in 2017. And this is one of the things that we will look with this satellite. Another way to test general relativity is to test the equivalence principle, because I told you this is the basics of the fact that we have this metric theory. And there are many ways to test the equivalence principle. The most famous way of testing the equivalence principle is to take two different objects and let them fall in an external gravitational field to see whether they fall in the same way independently of their chemical composition and their mass. There is another way to test for the equivalence principle is to use the fundamental constant of physics. We can ask the question whether the constants, like the mass of the particles and so on, are actually constant. In fact, if they were not constant, it would mean that you can design, let's say the fine structure constant will be space-time dependent, you can design an experiment which will show a different result at different space-time position. You can do spectroscopy here on Earth and on another planet 10,000 years ago, and if the fine structure constant were different, you will get different spectra. So you can measure these things. So if the constants are not constant, basically you have a violation of the local position invariance. You can even show that you will have a violation of the university of freefall. And in fact, from a theoretical point of view, it just means that what you are calling constant, they are actually dynamical quantities which depends on the dynamical fields. So you can write such theories, and what you realize is that, well, if you introduce a dynamical field, then your fundamental constant will become also dynamical quantities, and if this field is light, then you will also have a long-range interaction. This is why you will have a violation of the university of freefall. And this is a very generic prediction from most high-energy theories of gravity. When you have extra dimension and string theory, for instance, they do predict that constants should vary. And so there are today a lot of constraints on these things. This could be a very long seminar in itself, which I will go just with one slide, actually. We have many systems that we can observe for which we can put strong constraints on the time variation of the fundamental constant. We can use Yoclo phenomena, we can use meteorite dating of the solar system, we can use quasar absorption spectra, the CMB, BBN, and we can combine them basically to say that today there is not a single hint of the variation of a fundamental constant. What is important is that this morning we were told that we can just play and let one constant vary just to see what is the effect. This is very important to do that. But actually you cannot just let's take one constant and let it vary, assuming all the other are constant. I mean, there are many reasons for that. And one of them is unification. If you have the 3-gauge coupling and you have the renormalization group, if you have a unification, well, if one of the gauge coupling is varying, then all the gauge coupling are varying. Also, you can, once you do QCD, the QCD scale will be related to the strong coupling constant, which means that, for instance, the mass of the proton, which will depend on lambda QCD, will also be time varying. This implies that the Yukawa coupling and the X-VEV will be dynamical quantities. And so you see that if you assume that one constant is varying, then actually what you have to do is to assume that all the constants can vary. So these effects are usually ignored because they are very difficult to quantify, but I think they are very important to take into account because sometimes you get cancellations and sometimes you get enhancements. So if you just assume that the fine structure constant is varying, then you may get very strong constraint on the time variation of the fundamental on alpha. But actually, if you take this framework, you can show that for some system, it's almost non-constraining, which is very important. So today, here is a typical level at which we can constrain the time variation of the fundamental constant on cosmological scales. So this is basically on the left panel, the relative variation, so in logarithmic scale. So basically, we know that the fundamental constants are not varying by more than 10 to the 17 per year here locally on Earth, and this is done by comparing atomic clocks. We know that on a 2 gigayears time scale with the Yoclo phenomena, it's not varying by more than 10 to the -7, and so on and so on. So this is the further we go, the smaller the constraint, and one of the reason of this is that if you want to interpret CMB data or BBN, you need a cosmological models, and these cosmological models depend on parameters, like the radiation content, the value of the curvature, and the matter constant, CDM. And these parameters are not known better than the percent level today. And this is why you get such bad constraint, because you have degeneracies. Which one? Ah, okay. So there are two bars. The first one is, so the one on the right is the constraint we have today. And the one on the left is the one we can expect to have, let's say, within 5 years from now, with all the progresses which are on the. And also you can use new systems. For instance, you can use stellar dynamics, like population 3 stars, and we hope that this is a good way to get constraint in this, what is called the dark age, where we have almost no information about the universe. So this is very, very promising. So I think that today there are a lot of ideas to test general relativity using the large-scale structure, like using weak lensing, and this has become a kind of mainstream activity because of the Euclid satellite. We can test the equivalence principle, and the use of fundamental constants is really fascinating subject. You can also use the nonlinear dynamics, because if you enter the nonlinear regimes, then you will test the nonlinear structure of general relativity. And even though the CMB can be understood by linear physics, you can test for non-Gaussianity, for instance, and then you have some hit on the nonlinear structure of GR. And one of the work I did with one of my students, Cyril Pitrou, is that we think that if the Planck data are what they are supposed to be, going to a multiple of L over 2000, we may we may see the nonlinear structure of general relativity at work by measuring non-Gaussianity, which is very interesting. And also you can use gravity waves. So we don't have gravity wave detector today, but it's very important because there are many theories in which you have different metrics. So light and gravity waves may not propagate on the same light cone, they may not have the same causal structure. So we can test, let's say, if you have a supernova and you observe neutrinos, photons, and gravity waves, you can ask yourself whether the arrival time of all these messengers are compatible with the fact that they propagate in the same metric, and so on and so on. So there are many ideas around, and I would bet that within 10 years we will have a better understanding of the domain of validity of general relativity than what we have now. And this is very important because this is a key ingredient to construct a cosmological model. So let me talk a little bit on the Copernican principle, the fact that we are picking a solution which is spatially homogeneous and isotropic. And for many years, in many books, even books by Durand and myself long ago, we were saying that these things cannot be tested because you observe the universe from only one point of space-time. So now there have been many ways, ideas coming around to test this hypothesis, and one of them on which we have been working with George is the fact that, of course, we observe the universe from one point, but I think we forgot we were relativists. I mean, we observe the universe from one point, but at different time, today and tomorrow. And we can ask yourself, do we get, I mean, the light cone, the past light cone I have today and I will have in 10 years is not exactly the same. Can we use this information to say something on the Copernican principle? And actually, there is a way to do that. So if you observe the universe at two different times, T0 and T0 plus delta T, you can observe an object, and if you look at its redshift, it will change with time because it's given by the intersection of the world line and the past light cone. So you can ask yourself, what can I learn from this quantity? So this time drift of the redshift is a very tiny quantity. Actually, it was computed first by Sandage in the 60s, and he got the numbers that a redshift shouldn't change by more than 10 to the minus 10 on a 10 years time scale. And he said, this is a very good point because I can do cosmology. Things will not change, on human scale. On a century, this number is far beyond all the precision I can get with telescope and spectroscope of the time. But on the other hand, you see that if you are able to measure z dot as a function of the redshift, then you have a direct measure of the Hubble rate as a function of the redshift. So it's very important to reconstruct the dynamic of the expansion of the universe. It has driven many people to try to see whether it's possible to measure this quantity. What we have understood is that if you try to compute this quantity in a universe which is inhomogeneous, you have an extra component which is coming from the anisotropy of the Hubble flow. So this term, which is sigma of z, and which has to be 0 if the universe is strictly homogeneous. So you see that if we are able to measure this quantity, we may constrain the local anisotropy of the Hubble flow and so control the homogeneity of the universe. So the goal is to use the project of the extremely large telescope, which are 40 meters telescope, and to use ultra-stable spectrograph. So you see, this kind of project now are discussed by ESO, and people think that in 25 years from now, they may exist. And of course, you need to wait for 25 years for this project to appear, and then you need 10 years of observation, which is a long time scale. But you have extra information that is not used today to constrain the cosmological models. And this is very important. For instance, there have been a huge debate on what are called void models, in which instead of explaining the late time acceleration of the universe by a cosmological constant, you change the geometry of the universe, you don't have an acceleration, but you have a local void. So what we did with, in particular with Peter Dunsby, was to try to take two of these models which cannot be distinguished by current data. and see whether they can be distinguished by this new observation, and this is what we get. You have the two models. So the black line is the standard model with the cosmological constant. The error bar as the one you inferred from this project on the LT, and you see that the signal you will get for this quantity Z dot for the void model is far away from the one that you get for the standard model, which means that these two models cannot be distinguished together, but with this new piece of information, they can be distinguished. So I think this is what is important, because if we think of the progress we made on our understanding of the world, there are two things. We make progress in mathematics, and you gave us just some example like a couple of minutes ago, but also each time we have better technology, we can make new observation. I think it's very important to try to see how we can use this new observation to put new constraints and to ask new questions on our universe. So topology. Topology is whether we can have some special shape of the universe and whether this is something we can detect. Interestingly, if you think of a topology, the best way to think about this is to take a box. This box has faces, and you will glue the faces together, so you will get a compact manifold. So here is a box which is a little bit strange, but the boundaries do not exist, so light can go around this universe. And if you put a galaxy inside the universe, in this box, then you can see many images, topological images of the same galaxy. So here is a simple example of a very small universe in which you just have one galaxy, and on the right you have the sky that will be observed by an observer living in such a galaxy. So you see, he will see his sky with many galaxies, and because they will not be seen at the same time and on the same angles, they may not look the same exactly. So of course, here, if you are smart enough, because there is just one galaxy, it's very easy to recognize that there is some kind of pattern in the sky. But imagine that you have like some billion of galaxies in the box, and you have this topological structure. How can you look for such patterns? That has been one of the things we have been looking at for many years. So it's a good method, but the point is that, of course, galaxies are not going so far away, so you will not be able to probe large boxes. There is a better idea is to use the cosmic microwave background temperature anisotropy, because if you have a topology, basically there are some places in this sky that you observe in two directions. And it's called the circle in the sky method, and it has been used with the WMAP data to conclude that the size of the universe should be larger than 85% of the size of the observable universe today. So we hope that with Planck, applying the same method, we can improve this quantity, but you see, it cannot probe a box which is larger than the size of the observable universe. There won't be any signal. So we try to say, well, can we try to probe the universe on the sky which is larger than the size of this observable universe? And there is actually a possibility, because if you have such a topology, you have a violation of global isotropy, which means that your CMB fluctuation will have a correlation which will not be diagonal. So if you have just isotropy, what you will get in this picture is just a line. And you see all this chessboard structure are a signature of the fact that because you have a topology, just some modes are excited. You cannot excite all the modes. You just excite the modes which are compatible with the boundary conditions given by the topology. And what we have tried to do is to say, well, how far can we get a signal? And we have used a statistical estimator, which is called the Kullback distance. And basically, if this thing is larger than 1, it means that you can distinguish two models. And we ask the question, how large can a universe be and not be distinguished from an infinite universe? And basically, you get something which is, let's say, 10% larger than the size of the last scattering surface. So which means that if the Planck data are good enough, we may be able to put constraints on the size of the universe on scale which are larger than the scale of the last scattering surface, which is kind of interesting because we are always thinking of the size of the last scattering surface as the size of the observable universe, so maybe we can constrain things beyond the observable universe, which is kind of funny, I mean, in terms of words. So this is what we hope to do in the coming years. As we discussed this morning, we have laws, but we need to know initial conditions. We have perturbations, we have thin galaxies, and this is coming from the dynamic of gravity. We need to know something about initial conditions. And in this model, the initial conditions are given by the so-called inflationary model. And as Michael Heller told us this morning, it seems that when you look at the sky, there seems to be an horizon problem. And I think that was one of the main motivations of inflation, is to reconcile some observation which look non-causal with a causal description. So the idea was to add a new phase in the history of the universe, which is an exponential expansion of the universe. And if you have such an exponential, basically the size of the universe is increasing faster than the Hubble radius, which means that basically you just observe a small patch of the universe, and what you think is not causally connected is actually being causally connected. So the question is about the initial condition. So this inflationary models has been introduced to justify the Copernican principle on observable scales, and it gives us an illusion of non-causality. What is also important is that it erases any dependency on the initial conditions at the onset of inflation. Well, not always, because if you look at the dynamics of this, the inflaton field during inflation, you have such a phase portrait, and you see all the trajectories, there is an attractor to the dynamics. And in order for the prediction of inflation not to be dependent on the initial condition of the inflaton field, you need the inflationary phase to last long enough. And this is one of the constraints. Otherwise, you will have to deal with all the trajectories, and your cosmological observation will be dependent from these initial conditions. What is also interesting is that this inflationary dynamics, it drives the universe toward a Friedmann spacetime. So it erases all this anisotropy and curvature. But in fact, imagine that you add some anisotropy and you go backward in time, because anisotropy decays faster than the energy density of the inflaton. It means that it will always dominate in the past. So it also means that if you take a simple example of a Bianchi-1 universe, which is an homogeneous but anisotropic universe, then you go backward in inflation, and the shear, the anisotropy will always start to dominate, which means that the number of E-folds that you have is constrained. You cannot get a large number of E-folds. And this is very interesting because it shows that there is a limit in the robustness of inflation. If you are in such a case, then you cannot even set the initial conditions the way we do it in the standard cosmology, and there may be a dependence on this initial condition. So this is something which we now are trying to test. Is there any hint of deviation from isotropy on primordial anisotropy during inflation? Because if you have such an anisotropy, then it means that maybe you cannot trust the standard way you do your inflationary predictions. Okay, and now this is I'm taking risk because I'm not specialist on that, but we have been discussing a lot of time with George, and I've tried to ask myself about, well, we have this universe and this picture of the hot Big Bang, and you see, if I have 20 minutes after the Big Bang, the universe is so hot that I just have protons, neutrons. I mean, with just 3 protons and neutrons at 10 to the 9 MeV, it's very difficult to imagine to form structure and to code information. If you go even beyond, you don't have this neutron and these protons. So when can some complexity emerge in the universe? So here is again the hierarchy proposed by George, and I think it's nice to split it in 2 parts. I mean, the 1 to 5, they are the same. I mean, it's basically fundamental theory, particle physics, nuclear physics, atomic physics. Then there is chemistry, and I think there is, I mean, I'm not a chemist, but it seems that there is 2 kinds of chemistry, like physical chemistry and organic chemistry. And then you have 2 paths. From organic chemistry, you can go all the way from biology to, let's say, sociology and everything. And on the left path, it's more like you are entering nonlinear regimes, and you will form bound objects, which like planets, stars, galaxies, and so on. And you see there is a huge difference between the two branches, because in the right branches, you have emergence of something that we call information. And this information has been discussed by George as the possibility to have this top-down action. But you see, to have some structures that can store this information, you need to have complex structure, and they can exist. I think they can exist only at low temperature, low density. And when they start to emerge, I think there is something I wrote, matter does not matter. What I mean by this is that if I take my, like fundamental particle, they are undistinguishable. I mean, there is not a single way to make a difference between an electron and another electron. So we can even think that I can take all my particle and exchange all my electron, my proton, my neutron with the one which are composing me now, and I will be the same person. So it seems that matter doesn't matter in a sense once you have, I mean, in terms of the way information expresses itself. And on the left side, well, you have you need this structure to form, and you have an inhomogeneous universe. Also, what is interesting is that the step 1 to 5, they are basically summarizing the thermal history of the universe and the fact that the temperature is dropping just due to the expansion of the universe. And once you have this cooling down of the photon bath, well, you have mass thresholds and you have some physical phenomena that can appear that were not possible, I mean, that can express at some time. So one of the questions is when and where in the universe can a given level emerge? So here is a plot where I've depicted the temperature of the photon bath as a function of the redshift, and you see it's decreasing as 1 over 1 plus z. And if you go very close, I mean, at very high redshift, where the temperature is such that you can't have any particles, and we are in a regime where we actually don't know the physics. It could be inflation, it can be some kind of quantum gravity era, we don't know the physics, it's some fundamental physics. After the reheating, we know that we have particles, between particles are produced during reheating, and there is a the temperature of the reheating is a key parameter here. Then if you wait, you will have Big Bang nucleosynthesis, and you will start to form nuclei. So then you will have light nuclei like helium, deuterium, and basically you will not go much further than beryllium. I mean, you will have some carbon, but it's, in abundance is 10 to the minus 21, so you cannot do anything with this carbon. But still, the universe is so hot that all the matter is ionized, and you cannot form any atoms. You have to wait for decoupling for atomic physics to be possible. Okay, beyond that, you don't have any atomic. And so you will have atomic physics at a temperature below than the one of the CMB, and then you have to wait for the first stars to appear because you want to have a large range of chemical elements like carbon, oxygen, nitrogen, and so on, if you want to do interesting chemistry, because chemistry with just hydrogen and helium is a kind of poor chemistry. Also, what is interesting here is that when you go to the lower redshift, the universe for the first step can be described as homogeneous. And then you have the formation of the large-scale structure of the universe, which means that the local density will be different in different zones of the universe. You can be in a very low density zone, and in this zone, you will just have atomic physics. You will never form bound objects. And if you don't form bound objects, you don't have stars, and you don't have planets. And most probably, you will not be able to go to higher levels. On filaments, you may have some chemistry. We know we observe some organic molecules in quasar absorption spectra, so we know that they are there. And just on very special places, you will be able to form stars, galaxies, stars, and planets. And this is what you need for the right branch, I mean, to develop further out. So now if I see what happened when I go from a level of complexity I to a higher level of complexity, as soon as I mean, if I am with this, the causal structure of the level 1 to 5, I mean, they are the one of fundamental physics. So basically, they are given by the Lorentz structure. This is special relativity. So basically, if I want to determine the physical condition at a given space-time point, what I need to know is the initial conditions in a patch which is at the inside of this path light cone. And now, at this point, it could be that the temperature will drop before a given temperature, that the density is in such a range that I have the emergence of complexity in information. So now, we like to ask the question that George was pointing out, when does this information is able to back react on the lower levels? Well, if I forget now, I don't know anything about this higher level of complexity, but I would say that if it derives in some sense from the laws of physics as we know them, it needs to be, it signs a path light cone. I mean, there is a kind of causal limit which is coming from the one of the fundamental theory of physics. But of course, what you expect is that actually the zone in which you will be able, this new phenomena, will be able to retroact is much smaller than the one of of the causal limit, because what I think is that the way this new phenomena will propagate is probably at a speed which is much smaller than the one of the speed of light. I just think, like, for instance, if I want, as a human being, like life, to retroact on a planet, you need to be able to, to go to this planet, and this is not something you can do at the speed of light, and it will take a lot of time. So basically, what you expect is that this higher level on the right of the right branch, they will be localized on very specific points, which are basically a point-like structure inside galaxies, and appear only at late time. So, for instance, the information you get from that is that there are some higher level complexity that will not affect, for instance, the understanding of the intergalactic medium, and so on and so on. So when I said that what is interesting when you have a model is to know what kind of physics you have to put in the models, it tells you that when you ask a specific question, you can determine which level of complexity you have to use to answer your question. And this is where I will stop, sorry. So as I said, we have a standard model which is extremely efficient, and it relies on a very small set of very reasonable hypotheses, which I summarized before. And but the only problem is with this dark sector, which is the center of a huge activity today, and people are trying to try to understand this dark sector, and it has led to a huge development of testing of general relativity, testing the Copernican principle, and all the other hypotheses of the cosmological models. And I think the thermal history of the universe is basically the first step to the understanding of this emergence of the higher complexity levels, and it works very well for the left branch. I mean, we understand how we form large-scale structure, we understand how we form galaxies, we don't understand, how we form smaller scales, like planets is something much more difficult. But this is all about inanimate matter, and to understand the right branch, it requires the understanding of when information appear and plays a role in our understanding of the universe. Because information is not like a new field that we can add in an action. This is something that we have to understand. What is the relation between the other components that we are using in fundamental physics? And this space-time analysis of the emergence of complexity basically is a way to characterize a system for which it can be neglected, and the system for which basically initial conditions are completely irrelevant. So basically, when George this morning was asking the question about this plane, I know that, well, there the initial conditions are completely irrelevant. But if I am asking a question about the distribution of galaxy, I guess like sociology is completely irrelevant. And this is, you can say what is relevant to answer which kind of question, which I think is the first thing you want to know when you address a physical question. And I will stop there. Thank you.
Thank you. And Jean-Philippe, typically very beautiful talk. Could we go back to where you were talking about testing the field equations? Way, way back.
Ah, yes.
I'm puzzled by one thing there. Where you were talking about the lensing as opposed to the other...
Here?
Yeah.
Here?
The next one.
Okay.
Yeah. So you look at the distributed gravitational potential, look at the distributed dark matter. Surely, isn't what we do when we find they don't fit, we say we've got dark matter?
Okay, so... This is a very simplified version because I didn't want to put too much equation, but this is a good point. If you take a catalog of galaxy, what you see is luminous matter, and you don't see the dark matter. Okay, what causes the source of the gravitational potential is the whole content of matter, standard matter, luminous matter, and dark matter. And here on the right-hand side, I put this delta, and I say, well, you can estimate what delta is from galaxy catalogs, but there is this problem which is called the bias problem. Does luminous matter trace the dark matter? And you see here, I have two observations for two quantities, which means that if I want to say something about this bias, I can't. The point is that if you add this bias as an independent quantity, and if you are able to measure weak lensing in galaxy catalogs and the velocity of these galaxies, because the velocity of the galaxy will be dependent on the gradient of the potential, you will be able to put a constraint on the bias. So you have three functions and three observables. But I didn't want to go too deep because it starts to be too much equation and technical, but you are able to do that. And I think this is the understanding of the fact that the measurements of galaxy catalogs with high quality and the determination of the velocity and weak lensing is a way to test general relativity is now completely admitted.
Two questions. First, very elementary. When you had that table, the two bars down the left, and George asks, what does the brown one on the left mean? I'd like to ask, what does the one on the right mean, in particular the 10 to the minus 17 associated with atomic clocks?
Okay.
I understand the ones of sort of 10 to the minus 3, that means that's the change you expect over that cosmological epoch. What is the 10 to the minus 17? Since atomic clocks were invented, the cesium clock, or since the best ones in Boulder?
That's a very good question. So, of course, you have cesium clocks. This is a way to realize a second. So, in any, this is the first clock you have. But you have clocks with different chemical composition. You can take rubidium clocks, you can take hydrogen clocks, and so on and so on. So now, since it started about 10 years ago, mostly because of these questions, people are constructing atomic clocks based on different transition, hyperfine structure, and different kind of atoms. And basically, when you compare two clocks, the ratio of the two clocks, whether there is a relative drift of one of the clock to the other, depends on a different combination of the fundamental constant. And it will be basically ratio of mass of the electron to mass of the proton, fine structure constant, and the gyromagnetic factor of the proton, basically. So if you compare these two clocks, you can put a constraint on the time variation of these quantities on a time scale of, let's say, a year, 2 years.
I'm delighted. I find it was a much better question than I realized.
The 10 to the minus 17 is amazing.
Yes, fantastic, isn't it? Now, I've got a second question, which was, does the binary pulsar and its fantastic agreement of the prediction of its energy rate of loss put any constraint on bimetric theories with different propagation speeds? Is it not the case that I heard somewhere that the speed of light occurs to the 5th power in the expression for the energy loss of the binary pulsar. Does that put a constraint on different propagation speeds of light and gravitational waves? Because presumably the binary pulsar is losing its energy. Everybody believes that it's losing its energy through gravitational waves. So would that put some constraint?
I don't know. I've never seen any work on this, so it's a good point to see whether there is a possibility. The point is that you don't see the gravity wave, you just see the energy loss.
Of course, yes.
And
not yet.
Yes, exactly. But I don't think the precision will be, enough to I don't know. This is something that needs to be thought of. I've never seen any work on that. Maybe you know.
As I recall, it was more a question that some of the bimetric theories, some of the key bimetric theories have dipole gravitational radiation.
Okay, so this is much worse.
And so it's much worse. And so I think, as a matter of fact, it does rule out quite a few of the bimetric theories. I'm not sure if it rules out all of them, but it rules out many of them simply because, the general relativity has quadrupole radiation and no dipole or monopole gravitational radiation. And so
but there are many, like if you think about the latest Bekenstein model to make a relativist version of monde, this is not constrained by this kind of problem.
Maybe not.
And then, there was an estimation, basically, if you feed the theory to explain galaxy rotation curves, and if you take a supernova like the SN 1987A, so the standard supernova, you expect a 4 days time delay between gravity waves and photons. I don't remember which one arrived the first, but 4 days is something that you will see easily in the data. So.
Non-commutative geometry, the spectral action. So we can do the same thing for biometric theories. So it is doable.
Thank you.
Any other questions?